Hello and welcome to our 8th lecture of Introduction to Mechanobiology. So, in the last few lectures I had discussed how rheology of ECM networks has huge importance in dictating their mechanical properties and in shaping the overall responses of the cells. Okay. So, one of the important properties of collagen networks or many biopolymer networks is this aspect called stiffening, strain stiffening. Okay. So, the more you deform, the more difficult it is to deform. Okay. And I argued that this is an inbuilt property that ensures that these tissues or the networks do not get damaged as a consequence of forces, okay? Because the more stiff it will be, it is going to be very difficult to deform it anymore. Okay? I will discuss about another procedure, another way in which nonlinear elasticity can be embedded or incorporated into the function at the single protein level. With that, today I will first discuss this protein called fibronectin. Okay. Fibronectin. Okay. So, fibronectin is one of the most important ECM proteins. Okay. It forms dimers, okay, of two similar polypeptides. Okay. So, notable in this molecule is this sequence of RGD, which has been shown to engage integrins or participate in mediating cell matrix adhesion. Okay. So, fibronectin is known to bind to multiple ECM proteins, including collagen. Okay. It also binds to other fibronectin molecules and proteoglycans. Okay. So, it is of key relevance to multiple cellular processes, including migration, wound healing, and differentiation. Okay. So, if I were to draw approximately the structure of fibronectin, so you have these three modules, and there is some extra, and the disulfide bonds are actually at this end, okay, and you have the same thing repeating here. Okay. So, binding, so many of the bindings, so if I particularly look at this module FN3, it has, so FN3 has 15 individual domains which fold by themselves. Okay. So, the question here is, and of these 15 individual domains, one of these, so domain 10 contains the RGD binding site. Okay. So, this RGD is actually hidden within this structure. It cannot be recognized by integrins directly, which means that for this binding site to be exposed, it must unfold. So, what this means is fibronectin has to unfold for exposing RGD motif. Okay. So, this has to unfold. Now, you have studied in biochemistry that unfolding can be done using, let us say, agents like urea or by temperature. Okay. You denature proteins using temperature. But what is it that leads to unfolding in vivo? So, what it turns out, it is actually forces exerted by cells, okay, which unfold individual modules, and this unfolding exposes cryptic binding sites. Okay. So, exposure of cryptic binding sites okay, via unfolding okay, triggers binding of FN3 modules to other molecules. Okay. So, it is unfolding, right, and how is this unfolding achieved? Via forces, okay, mechanical forces exerted by cells. Okay. Expose cryptic sites. So, this raises a possibility. So, you have FN3 module okay, which has these domains 1, 2, 3 up to 15, and out of this domain 10 contains the RGD motif. Okay. So, for the same molecule, imagine you have 3 different types of cells which have different capability to exert forces. So, depending on the amount it exerts, amount of force it exerts, it is possible that one or more of the cryptic sites are exposed. So, the magnitude of the force will influence how many of these binding or cryptic sites get exposed, and since exposure of cryptic sites opens up this binding of other molecules and activation of signaling transduction signaling cascades, this would mean that the magnitude of force can influence the signaling cascade which gets activated. Okay. So, in an attempt to understand how these individual domains are sensitive to forces, okay, experiments were done, temperature denaturation experiments were done, and it was found, for example, that FN3, so your third domain of FN3 roughly denatures at 120 degrees Celsius. Okay. So, compared to that, the sixth domain of FN3, it denatures at denaturation temperature. Okay. The sixth domain of FN3 is around 111 degrees Celsius. Okay. Similarly, 10th domain of FN3, okay, which contains the RGD binding sites, unfolds at denatures at 102 degrees Celsius, so on and so forth. And in this way, so the weakest among the weakest domain is the 11th domain of FN3 module, okay, which denatures at 48 degrees Celsius. Okay. So, this tells you that there is a gradation of sensitivity of these individual domains to denaturation. Now, if a domain which unfolds at a higher temperature, this would suggest that this domain is much more stable than any of these other domains. Okay. So, this would indicate that domain 3 is among the, it is a strongly folded domain, okay. And domain 11 is a weakly folded domain, okay. So, one of the challenges of this is of course temperature denaturation need not necessarily give us a clue of whether the same holds true for in vivo situations. When these molecules are exposed to forces, will they unfold in a similar manner? So, this calls for a technique which we can employ for tracking the unfolding dynamics of the whole molecule and understand what is the strength of individual folded domains. Okay. So, one of the techniques which has been employed exhaustively for studying the unfolding dynamics of various proteins is atomic force microscopy. Okay. This in short it is referred to as AFM. Okay. So, originally AFM was discovered as an imaging tool. Okay, it was discovered as an imaging tool. However, in addition to imaging, subsequently it has found wider uses in other techniques, one of which is, for example, probing mechanical properties of cells, tissues, etc. Okay. And it has also found use for studying unfolding of proteins. Okay. So, let us see what exactly is an AFM, what does an AFM have, and how would one use an AFM for studying protein unfolding. Okay. So, if I were to draw an AFM, so what you have, okay, okay. So, these are tips. So, this is called the AFM cantilever. Okay. And this is called an AFM tip. Okay. It is called an AFM tip. So, you can have various geometries of these tips. So, for example, if you want to image something, your tip, so if I were to just draw the tip geometries, okay, you can have tips which are very sharp. Okay, you can have, this is let us say a blunt tip, you can have a very sharp tip, or you can have the tip is nothing but a spherical ball, sphere. Okay. So, the tip geometry. So, among the other things what you have is the tip geometry. So, this half angle is different in these cases. So, this sharp tip is much preferred for imaging purposes as well as protein unfolding purposes. Okay. This blunt tip is used exhaustively for probing mechanical properties of tissues, cells and tissues. Soft samples. Okay. While this sphere, so in comparison to the blunt tip, sphere is preferred for super soft samples. Okay. So, based on the overall geometry of the cantilever tip, what you also have is an effective stiffness of this tip. Okay. So, you have some spring stiffness, spring constant. Okay. So, if you are for you can vary the spring constant by varying the length of this cantilever. Okay. If your cantilever length is long, then the spring constant is high. Okay. So, long cantilevers have higher spring constant. Okay. So, for probing proteins, okay, for probing proteins or protein unfolding, you want, so K, the spring constant K has to be order 10 to 20 piconewton per nanometer. Okay. The spring constant has to be of this order, because the forces required for unfolding a protein domain might be of the order of tens of piconewtons. Okay. Okay. Now, let us see how does the cantilever operate. Okay. So, you have this is the AFM tip, okay, and what is done. So, the back side of this is shiny. Okay. So, you have a laser which focuses at this point. You have a photodetector, okay, and you send a laser light, okay, which focuses on the back of this cantilever and reflects off the back and gets detected by a photodetector. Okay. So, for example, let us assume that tip is trying to probe this particular substrate, which can be just glass. Okay. So, when the tip is moving through this air, okay, let us say this is air and you have a dry surface. This is a dry stiff surface. Okay. Example, just glass cover slip in case of biology. So, when the tip is moving through air, okay, the tip does not deform, right, because it does not touch anything. Okay. But as soon as it touches the surface, the tip deforms. Okay. So, when it comes and touches the surface, okay, so you have deformation of the tip. And this deformation is what is tracked by the photodetector. Okay. So, what is detected in the photodetector is in volts. Okay. So, you can have to use something called inverse optical lever sensitivity to translate volts to nanometer of deflection. Okay. So, the electric system detects everything in volts. And using, okay, so you can calculate something called inverse optical lever sensitivity. Okay. This is called involts. Okay. So, essentially finding out a way to calibrate volts with nanometer which tracks deflection. Okay. And also there is a piezo which tracks the position of the tip. So, you have this z axis, okay. The z piezo will track this position, tracked by Z piezo. Okay. So, if I were to draw a complete cycle, okay, a complete cycle. So, let us say this is Z position and this is deflection. Okay. So, you generate okay. So, this is a curve that you get as raw data from an AFM experiment. So, let me label some points. Okay. At point A, you are far from the surface. Okay. At point B, you contact the surface. Okay. So, in B to C, you are indenting the sample or surface. So, the extent of indentation of the sample and the deflection of the tip is dictated by the compliance of the substrate. Okay. And after you reach C point, so if you keep on banging your tip against the sample, then eventually at some point the tip will break. So, you do not want to do it. So, you limit the maximum deflection. So, okay. So, in AFM jargon it is called as the set point. Okay. And this set point you enter in terms, so set point is nothing but the maximum force beyond which tip should retract from the surface. Okay. So, from point C, so if I were to draw, this is indentation. So, from point A to B you are here, and from C, so let us say this is your sample. Okay. At point C you are going up. Okay. C onwards, C, D, E will be points on the way up. A and B will be points on the way down. Okay. So, this is called the indentation cycle. So, you have two parts, indent and retract. Okay. So, depending on what you want to measure, let us say you want to measure the mechanical properties of the cells, then you want to analyze A, B, C portion of your data. Okay. A, B, C is for quantifying mechanical properties. Okay. So, for doing adhesion, so let us say if I want to quantify adhesion or for protein unfolding, so I analyze the retraction data. Okay. I analyze the retraction data for experiments where I want to quantify adhesion or wish to quantify protein unfolding. Okay. So, that is clear now. So, in our case of protein unfolding, let us say I have a surface. Okay. If I were to, let us say I draw it like this, I have a surface and I have the protein which is anchored at some point. Okay. And you have this tip here. Okay. So, you want to, for protein unfolding studies, you want to operate at sparse concentrations. Okay. This is to prevent / minimize any aggregation. So, you want to operate at the single molecule limit. Okay. You want to operate at the single molecule limit. Okay. So, we will continue in next class from trying to understand how does the tip know where the protein is. Okay. Because if I am operating at the single molecule limit, I am working with a very dilute specimen. So, how will the tip know where my protein is situated, number 1, and then what is the signature of an unfolding experiment, okay, and how can I glean information about unfolding dynamics of individual domains within a protein. With that, I thank you for your attention and will continue in next class.